kind of centered on really the feebleness of the human brain. Right? The human brain can't deal with very large numbers or very small numbers. We just don't have the ability to process that knowledge. That's why when we look at the national debt, nobody's really concerned about it. It's like, well, it's only 13 trillion. It's not even 13. What is it now? 9 trillion, I think, is low. I think we're... But exactly. It's so big that I don't even care about it anymore. If that was your life, okay, it doesn't matter how much money I make. It's just going to disappear anyway. I'm not even going to worry about it. It's such a large number that we've lost all comprehension and all meaning behind it. So when people go through, oh, we need to be concerned about our debt, and you're like, yeah, whatever. Okay? It's too large for me even to deal with, even potentially coming up with a plan of fixing. Okay? We've ignored it. Okay? Same thing is unfortunately happening with moles. And the biggest issue behind moles is we can't ignore it because it's one of the things that defines chemistry. Okay? So we can't just get rid of it. We have to come up with some concept to be able to wrap our feeble human brains around that concept. And I believe in the video we talked about the farmer. Is that right? Eggs. The farmer and eggs. Okay, so we had that farmer that had 12 chickens, each laying 12 eggs per day or something like that. How many eggs do they get in a day?
72 chickens, 2 eggs.
Either way, we get 144 eggs, right? Any way we slice it. So if you go back to the farmer and say 144 eggs, you think, oh, that's not a big deal. I understand 144, why can't they? Right? And this, I'm not trying to mock farmers, but it definitely looks like that. Okay? If we say the farmer then can't comprehend numbers larger than 20, well, 144 eggs is now impossible for him to understand. Okay? Because that number is larger than 20. That is outside the realm of our understanding. We need to somehow change our understanding or change how we present that information such that he or she, for that matter, can understand it. Okay? And in the video, what did we do?
Make it into dozens.
We invented a new unit. We invented the concept of dozens. Okay? And within that, we can say, well, Mr. Farmer, or Mrs. Farmer, we can say 1 dozen is equal to
12 eggs.
12. 12 what?
Eggs.
Okay? So a dozen bagels equals 12 eggs?
We got to keep the same unit.
We have to keep the same substance behind this. Okay? So when we're looking at inventing this new term, it's really just a way to shrink a number down. It's a counting. Okay? It's not a measurement, it's a count. Okay? So if I look at a dozen eggs, that says eggs, that equals 12 eggs. What if I made it a dozen, for the lack of being creative, Skittle farts? It becomes 12 Skittle farts. So I can do a dozen of any substance, and that then relates through to any substance. Okay? And this is where we have to be careful. Are grams a substance? No, grams are a measurement. Can I go through and say a dozen grams is 12 grams?
Yes.
Technically, yes. But am I saying that as a measurement?
No.
No. What am I saying that as? I'm saying if I take a dozen of things that weigh a gram, that would be 12 of those things that are grams. Okay? The gram is a measurement. Moles is not a measurement. It's a numerical value. It's a count, okay, of an object. Kind of makes sense? Okay. So why do we go through and do this? Well, it has to come back to kind of our conversions. Okay. So we've looked at this conversion, and we even looked at, whoops. But let's go back through it and review, because we need help with those conversions, because we need to have a process that we trust when we move into this. That's the whole point of that previous unit, and hence kind of the retest with a lot of those calculations. We need a process for solving these. Our process says that we want this to equal Whatever we're trying to get. What are we trying to get?
Micrograms.
Our micrograms with that weird mu symbol. Okay? This question is formatted a little bit easier because what are we given?
Milligrams.
Okay? How many things are we given?
325.
Fair enough. How can I phrase that differently? 1 was the answer I was fishing for. We're given one thing, which happens to be 325 milligrams. So if we think back to the dimensional analysis, we say, well, what are we given? We just put that on the left-hand side. Well, some of the more advanced problems, what happens? Are you given just one thing? No, you have to do an interpretation on which one thing you want to use to begin with. Okay, since we're only given one, we can just make that assumption right away. I already forgot. Milligrams was what we were given. We started with 325 milligrams. We said, well, is milligrams the same thing as microgram?
No.
No. So what has to happen?
Conversion.
I need to do a conversion where the milligram unit disappears. Okay? So it has to show up on the bottom. Ideally, what do I want showing up on top?
Micrograms.
Micrograms. Because that would be a one-step conversion, I have my answer. Okay? For those of you who are good with powers of 10, shh. For the rest of you that aren't good with powers of 10, do we know the direct conversion between milligram and microgram? No. So we have to go through some other conversion factor. So what conversion do you know how to go from milligrams to? Okay. Hopefully you know how to go into grams. Okay. And that's because we're doing a metric conversion. We're just changing our powers of 10. Milli meant, or means, 10 to the negative 3. Our power of 10 is associated with our core unit. Our core unit is our grams. And if we looked at our unit system now, we'd be in grams. Is grams what I want for an answer? No. So I have to do another conversion. I want grams to be in the denominator so that the unit can cancel. What do I want to convert those grams to? Micrograms. Okay. And again, we'd ask the question, do we know this? Well, this is one we weren't required to memorize, but we could look at the front of the test and say, oh, micro meant 10 to the negative 6. 10 to the power of 10 is associated with which unit? The core unit, which is the core unit. Grams. What happens to the gram unit? It cancels. What unit would I be left with?
Milligrams.
What unit would I be left with?
Micrograms. This is
Micrograms.
just using it.
Okay. It's okay, but you're potentially on the audio, so we're at micrograms. Right? That's what I want for an answer. Okay, so I'm done. Now I have to enter it into the calculator and go through and punch those things in. There's been some question about how you would enter this into the calculator. Everything in the numerator is just a multiplication. 325 times 10 to the minus 3 times 1. Everything in the denominator is a multiplication. 10 to the negative 6 times 1. What's in the denominator of 325? A placeholder one. I don't like arbitrary, but I know where you're going. Okay, a placeholder one to make sure that we know there isn't anything in the denominator that changes the meaning of the 325. Right? So I could go through and include that. It's not going to affect anything because it's 1. So I take everything in the denominator, or top, multiply that through in the calculator. Okay, it spits out an answer. That answer that it would spit out would be 0.325. Yeah? Yeah? Okay, and then I would divide that by 10 to the negative 6. Okay, because the 10 to the negative 6 is in the denominator. This is a fractional system. I enter that into the calculator and it spits out a final answer of 325,000 as our answer. Okay? Notice in that work, how many units are there? I know that was a vague question because you could say in that work, there's lots of work up there. In the work we just drew with the numbers in our calculator.
0.
I didn't show any units. Okay? That is actually okay. Why is that okay? Where did I get those numbers from?
From the units
from the system up top. I already solved that the units come out correctly. I'm now just dealing with the mathematics behind it. Okay? What I've seen or saw, Sue, I have seen, past tense of see, saw. What a lot of you did was just jump to the calculator work. Okay? That works if you put it into the calculator right, okay, and you've placed the numbers correctly. More often than not, you've placed the numbers incorrectly because you didn't have the unit work to tell you where to place the numbers. What you had was some internal mechanism in your head saying, oh, I know how to do these conversions, so I'm just going to do what my head tells me to do. Okay? For a system like this, where you've had experience with that, I mean, you're probably plus or minus 20 years, maybe plus or minus 15 years. If you think about when you started dealing with calculations and relationships, right? You've spent 15 years doing that internalization, right? As soon as we move into moles, you can't internalize anymore. It's now in that stupid numeric that our brain doesn't understand and we just ignore. Right? So if you're going to start ignoring the meaning behind our stuff, then you need a process to allow you to solve, to tell you where to do the calculations instead of having that internal system. Right? That's all we're trying to do within Unit 2. Because as soon as we move to Unit 3, which is our next step, things are going to go haywire and we have to rely on a unit system to allow us to navigate. Right? Kind of makes sense? Yes?
I had a question. Instead of doing it that way, it seems a lot of work. Can you just
Okay.
do it like 1 milligrams over 1,000 micrograms and then just set it up in small?
So 1,000 milligrams is 1 microgram.
What's that?
You said 1,000 milligrams is 1 microgram?
1 milligram.
1 milligram
over
is
1,000 micrograms.
1,000 micrograms. What did you just relate?
Something short of me.
Milligram to microgram. You knew that. Okay? So that's great for Unit 2. That's awesome. You knew that. How comfortable are you with 6.022 times 10 to the 23rd? Okay. Don't do that then. Okay? And it's not that it's wrong. You're right. Okay? But the issue is you're using a method that you've internalized that you can't use anymore. You can't internalize this. You have to put it on paper. Okay? So try to avoid skipping those steps. Okay? That's the point of the unit method. Okay? Mathematically, everything works out the same. Even your units work out the same because you memorize that unit swap. If you're in a system that you can't memorize that unit swap, you're dead in the water. That's the point of this method. Okay? And I know everyone's fighting me on it. That's fine. Okay? Because you're like, I know how to do that. Why are you telling me? Okay? I'm telling you because when I move up to the system, mole is 6.022 times 10 to the 23rd atoms. How many oxygen atoms are in 0.240 moles of O2? Take your swing at it. Use your method of internalizing and see what you can come up with. Okay? Seriously, do it. Okay? See what you can come up with for an answer. Okay? Show whatever work you want, and then we'll go ahead and take a look at what I would go through and approach for this. Okay? There are a couple curveballs in it that you have to watch out for. Okay? So, I believe what you told me to do, Paul, was well, actually, you started with the 6.02, so let's run with that. 6.022 times 10 to the 23rd. And this isn't a judgment, by the way. Okay? It's completely irrelevant of judgment here. 6.022 times 10 to the 23rd, and then you said times 0.240. And then you said whatever that equals is going to be.
Should be how many atoms?
You should probably put 6.22 and all the way through 10 to the 23rd parentheses.
Okay. Because it's a multiplication, we don't have to worry about it. It's all multiplication. We don't need the parentheses. It's not a bad idea to get in the habit of putting parentheses around it to make sure that it shifts in the appropriate
For your
space.
calculator to work.
For calculator's sake, and again, it's all multiplication, so it's not going to matter. But the instant you do a division, you have to make sure that that 10 to the 23rd is partnered with the 6.022. Right. And there are a variety of ways to do that without parentheses if you want to talk calculator stuff with me after class. Okay? So what am I going to complain about? Yes.
the oxygen, what about your 2 oxygens, right? Well, you're gonna complain about you.
I'm going to complain about a couple things, yes. Okay. Whether my complaints are valid or not, I'll leave you to decide that. Okay. So one thing, we have 2 different formats for how we're presenting the molecule we're looking at. We're mole of O2, and it's asking for
Oxygen atom.
oxygen atoms. What is the formula for an oxygen atom? Oh, oxygen is a diatomic element, so that if I am looking at the element of oxygen, it is O2. Am I looking at the element of oxygen?
Yeah.
It very particularly says oxygen atoms, which means what I'm solving for is just O.
And that's O2.
Oh, yeah.
So
What's the problem?
It's O2, so everything has
It's O2. Minimally, what we've calculated in this system here is not atoms of oxygen, and this is where it's going to get a little bit weird in referencing, is atoms of O2. That's not what you were asked to solve for.
Can we
Okay.
divide by 2?
times the N2.
Okay, divide by 2, and this is where we're going to run with it, because it's that gut response that I'm trying to trigger on this. Okay, so now let's pause.
Times N2.
That's our work. Okay. The next thing I'm going to complain about is there's no units in that except in the answer. Okay. So the way you've manipulated and put those numbers in, okay, is from what you did in your brain. Right or wrong, it's in your brain. So a couple things with that. If this is a multiple choice question, and you're right, no complaints from me. Because it doesn't ask to show your work. If this is a show your work, you are going to get complaints from me because I want units. That's part of the show your work, is showing units. Okay? You could accept that as just a wash on the next exam and hope and the final is all multiple choice, so who cares? I don't have to show work. Okay? That's fine. Okay? I'm absolutely okay with that as long as you acknowledge that's what you're doing.
So just plugging in the units into this equation would not be acceptable because then it doesn't make any sense.
So that would be an interesting question. Can you just jam the units into this? You have to make sure to jam them in correctly,
It would be ridiculous.
which would mean doing it the way I suggested. What do we want for an answer?
Atoms of oxygen.
Atoms of O. What am I given?
Mole of O2.
0.240 moles of O2. Okay. Well, I know my mole relationship can get me into atoms. 1 mole of atoms. Officially, I'm using a bad conversion factor there. I should specify the substance. 1 mole of atoms is 6.022 times 10 to the 23rd atoms. Okay. So I need to get rid of moles of O2. And ideally, whoops, I want atoms of O. That says atoms, which I'll be erasing in a second anyway.
So,
When we're looking at our conversion, the substance must be the same. Is O the same as O2?
no.
No. So I don't have a direct conversion here. That's not a valid conversion. Can I convert it into something else, though?
Yes, you can convert it to
I could go... both technically work. We'll come back to that one in a second. We could go to atoms of O2. Atoms becomes a really weird reference here because O2 isn't really an atom, it's a molecule. Okay? So we can kind of float back and forth between using atoms and molecules as long as we're making sure the symbols for our substance are correct. Okay? So the English we can almost ignore as long as we're tracking the substance correctly. Because atoms versus molecules is just a way of counting whatever that object is. Okay? It's like counting men versus women. Okay? We're all people. So how do I apply my numbers into this? Okay? Well, what shows up in front of atoms? Go to the conversion factor. 6.022 times 10 to the 23rd. Atoms was 1 mole of O2. Dang it, Paul. That's looking pretty solid. Right? Mathematically, you're doing exactly the right thing. So in a multiple choice, you could be spot on Okay? But remember, we don't have the right unit yet. So we need another conversion. Atoms of O2 to
Atoms of O.
atoms of O. Where do I find that conversion factor? Where do I relate the atoms of O to the atoms of O2?
You just wrote it down. I mean, so to the periodic table.
Nope, there's no periodic table.
Memorize.
The part of you just wrote it down is darn close, but not close enough. Because we're hearing memorize, we're hearing periodic table, which are both wrong things. It's actually already up on the screen.
What? Oh, divided by 6.
How many atoms of oxygen are in O2?
2.
2. That's what that means. The 2 was associated with what?
Oxygen of 2.
The atoms of oxygen. How many atoms of oxygen are there?
2.
2.
Wow.
What did you do, Paul?
You divided this.
You divided by 2. The units tell you where to place the number. If you're used to doing a simple conversion, one step, you were spot on. The instant I threw in a second conversion, what happened?
Where'd the second conversion come from?
Because atoms of oxygen versus
Yeah.
atoms of O2.
Yeah, but understand that's fairly simple going from O2 to O. That's
And
just
it is
dividing.
absolutely fairly simple, which then proves my point further. What did you do? The wrong calculation. Every single one of our conversions is absolutely simple. A single conversion is simple, period. Multiple conversions, okay, if 99% of the time I get a conversion right, but I do 1,000 conversions, the odds of me making a mistake aren't 99%. It compounds all the way through. And the odds of me making a mistake after those thousands of conversions is actually significantly high. Okay? So the more we add in conversion steps, the more likely you are to make a mistake in your head. That is why we need to write out the units. That is why we do dimensional analysis. The single conversion you will absolutely, 99% of the time, get right on your own. The instant I ask you to do more than one, you start to shoot yourself in the foot. Okay? That is all I'm asking you to do, is to write it out so that you minimize those secondary mistakes. Yeah.
All right, so I understand what you're saying.
Yeah.
But you continuously don't do the last part. And so
What's the last part?
Right, like you're going to go to the next slide without solving the problem.
Okay, so solve it.
Right, and that's
Pull
what
out a
I'm saying.
calculator.
It confuses me when I don't see the answer.
Okay, pull out the calculator.
Right, that's, I got it.
I don't have a calculator.
I don't have a calculator.
6.022 times 0.240 divided by 2. If you want to throw in the 10 to the 23rd, you can.
Will 10 to the 23rd still be in our answer?
I should get it.
So that's the bottom one.
Yeah.
Sorry. I need to see that.
I
number
definitely
again.
didn't do the top one.
2 point, I need the top one too.
Oh, I did.
89056 times 10 to the 23rd. That's what the calculator spit out for the bottom. For the top, what did the calculator spit out?
Still getting there.
For the top, I got 7.2264 times 10 to the 26th.
You got 7?
I probably did it wrong.
That doesn't sound right.
The bottom we just won.
The bottom one's going to be divided by 2. Yeah, there you go. Or the top one. Oh yeah, you were right. 7.22.
It went down.
64.
It went down.
Oh, it went to 10 to the
0.
22nd. That was the
Yeah.
part that I missed. Okay. There's your answers.
That's a big.
Guaranteed both of those show up on the test. Okay. Is that a significant difference? That is pretty huge. Power of 10 off. That's the difference between making $100 an hour and $1 an hour. That's a lie. That's 2 tens.
Right. I
$10 versus $1.
All right, I understand what I did was wrong. Show me where. Where is it wrong?
Dividing by 2.
It's a divide by 2.
It's the divide by 2. What did we have to do? Where's that divide by 2 down here? You multiplied by 2. Why did you have to multiply by 2? Because your units tell you where to place the 2.
Because I multiplied up here, and then okay.
Okay? This is why the units drive this. Okay? It is very easy to make a simple swap on those numbers. Write out the units. It solves that issue.
So I need to divide .240 by 2 and then do it?
Talk to me after class. Multiplication, division doesn't matter when you do that calculation. Okay? Ultimately, moles 6.022 times 10 to the 23rd is a conversion factor that allows us to take atoms, which we can't see or weigh, and scale them into something that we can weigh and measure and observe. Okay? That's the whole point of the mole. Okay? Which means once we've established that this is what a mole is, we're done using it. Okay? We're done using the 6.022 times 10 to the 23rd. We can pretty much ignore it and just focus on moles. Because what we've done is scaled our reaction up enough that now instead of counting atoms, I can count moles of atoms. The mole is now an easier number to comprehend. If I looked at the debt as, let's just guess at some numbers.
23 trillion.
23, did you look it up for me?
I can.
Okay, we're going to run with 23 trillion, 4, 9, 6, what are we at? 1,000?
Yeah.
0, 2, 1, where are we, million? 0, 0, 0, I'm running out of creativity. There's billion, and then 5, 4, 3, dot, 2, 2. That's a really big number. That's really hard to figure it out. So what do we end up calling it? 23 trillion. What is trillion?
Really big number.
A really big number. Why did we invent the unit of trillion? To take that number that I'm like, oh my God, I can't even comprehend that, to take that really big number that I don't have enough fingers or toes for, to turn it into something that I could potentially count on my fingers and toes if I was mutated.
3.
Okay? That's the point of those trillion systems, or million, or billion. It's trying to condense that massive number into something more reasonable. That's what a mole is doing. It's the same thing. It's trying to condense that massive number into something more reasonable, so that when I look at running a reaction, I don't have to count atom by atom. I can count groups of atoms. Yes?
And just so I understand it correctly, there is no such thing as significant digits in this, right? Like sig figs don't play a part in this.
Sig figs absolutely still play a part in this. When we're running our conversions, notice that I've trailed out a whole bunch of significant digits on the 6.022. Okay? I went out to 6.022. I carried it to 4 sig figs. Why did I carry it to 4? You're usually 95% of the time responsible for carrying how many sig figs? 3. So if your conversion factor has 4, the conversion factor never affects your measurement. Your measurement is going to dictate your sig figs. Okay? So when you go through and run your calculations, pretty much once we've cleared sig figs definitively, we're now into just saying, I just want 3 sig figs. Okay? Which is horribly inaccurate. Okay? But it allows us to just kind of move on. Okay? Dust it off and just move on. It's wrong, but it allows us to change our focus to manipulate things a little bit more quickly and easily. Okay, so sig figs absolutely is important, but it plays a much smaller role, because what are we testing at in this next unit? Not sig figs. I'm testing at your ability to do these mole conversions.
Yay.
Okay? So, one of the things that came out of that video, okay, is looking at where that mole and that number of atoms, because we could have picked any number of atoms. Why did I not pick mole to be 100 atoms?
That's not what it is.
Okay. That's kind of a weird, why, I mean 6.022 times, why did I pick that specific number?
Because that's how many atoms you need to be a substance to be usable in experimentation.
It has to come back to scaling our usable amounts in an experiment up to a measurable system. If I picked 100 atoms, that mass is still like 10 to the negative 23rd grams. 10 to the negative 23rd, and we're already into problems because now we got powers of 10, negative, and stupidly small numbers. Our balances go to what precision in lab? 10 to the negative third. 20 times more than that was 100 atoms. We don't have a balance that could string out the zeros reasonably enough to get that accuracy. When you walk in the room, you notice the balances, that last number fluctuating every so often. You're like, these balances suck. These are horrible. No, they're actually insanely accurate. That's why they're fluctuating there. Because you breathe, you change the temperature. That change in the temperature changes how it monitors the balance, and guess what? It fluctuates. It's detecting your breath. It is detecting your body heat. It is detecting the air movement as you walk by. Right? We try to limit all of those things as best we can, but it's still detecting them. That's why it's fluctuating, not because it's a crappy balance. Okay? A crappy balance doesn't fluctuate. Okay? So we have really good balances. They aren't going to be even remotely close if we're dealing with 100 atoms. So someone went through, who's that someone? Actually not Avogadro. We just gave credit to Avogadro because he started to acknowledge and said there has to be a better way to measure these as opposed to atoms. We need some other system. He didn't actually define it. Somebody else went through and defined it and said, he was really the guy that said that we should do this. I'm going to give him credit and name it after him.
Oh, that's nice.
Yeah.
How is that named after?
How is it? We call it Avogadro's number.
It's in the reading.
I was gonna say mold.
Okay? So, big things that come out of this. Okay? The atomic mass on the periodic table. So nitrogen, what's its atomic mass? It's the red number under nitrogen was 14.0067. That is the atomic mass. What are the units on that atomic mass? AMU, which stands for atomic mass units, which is really just a fancy way of saying, I'm going to invent a unit system and call it that. Okay? Because it worked. That's based on the number of protons and neutrons that contribute to that, and that's how we get those averages. Okay? That's all the way back in, I think, Unit 1. Okay? So that is its atomic mass unit. When I go in to use the balances in lab, okay, what unit does it spit out? Grams, not AMUs. What is the conversion factor between AMUs and grams?
It's on the test.
It is on the test. It's 1.61 times 10 to the negative 23rd? 24. 1.61 times 10 to the negative 24. Okay? A really 1.61 times 10 to the negative 24 kilograms is 1 grams is 1 AMU. Okay? And you might, oh God, another number to memorize. How did you know that number? Did you memorize it?
I wrote it down from the paper.
Okay, wrote it down from the Playposit. Take a look at the front page of your exam. I'm actually not positive that it's on there, but it might be.
I'm pretty sure it is.
1.66 times 10 to the negative 24 grams is 1 AMU.
There it is. It's on the exam. You don't have to memorize it. Okay? Is the 6.022 times 10 to the 23rd on the exam? Oh, that's also on there. Interesting. Okay, I gave you both of those. That was kind of nice. Anybody know the relationship between those two numbers? One was to the negative 24, really, really, really small, and one was 10 to the 23rd, really, really, really big. But both those numbers are pretty close, right? They're just opposite directions. Like maybe if I took 1 over 6.022 times 10 to the 23rd, what would I get? I'm guessing that was a sigh of, oh, that felt nice as a stretch, not like, oh, that's amazing. Darn. Right? Oh, that's amazing. The inverse of Avogadro's number is 1.66 times 10 to the negative 24th. It's the conversion factor between AMUs and mass and grams. Okay? They are one and the same. They're used in different systems. Why did we pick that number? Because now I can go up to the periodic table, and for nitrogen, yes, it is 14.0067 AMUs for a single atom. But if I want to know the mass for a mole of atoms, I now have to adjust that number upwards. Okay, so let's take a look at that real quick. Let's just ignore the question that's on there.
Sure.
I want to know the mass in grams for a mole of atoms. Okay? Well, the number that's on the periodic table was for nitrogen, 1407 AMUs for nitrogen. So I heard something about 6.022 times 10 to the 23rd. What are you doing with that? Where'd you get that number?
Oh, it's just the mole number.
Oh, you said to multiply, right?
I think we should follow the.
Yeah, this is exactly what I'm fishing for. I think, quick backtrack, I think we should follow the unit system. Yeah, okay.
Follow the units first.
Okay, let's track this. AMU's nitrogen. What am I measuring?
Mass units.
The mass unit of what?
Nitrogen.
What about nitrogen?
Atom.
Atoms?
A single atom.
A single atom. So what I'm trying to do is take a single atom of nitrogen. So really this is one atom of nitrogen.
There we go.
Okay. Because that is the mass for that. That's what AMU means. Okay. It is the mass unit. So if we split up AMU, it's really mass unit nitrogen per atom of nitrogen. Right? And let's see. Did Wolf set this up right? 6.022 times 10 to the 23rd. What would our units be?
Don't be a mole of nitrogen. Atom of nitrogen.
Atoms of nitrogen. Why'd you say atoms of nitrogen?
Because it's a mole, so it's multiple atoms.
Okay. If we memorize our system, the 6.022 times 10 to the 23rd was associated with the atoms, not with the mole. Okay, so you placed the number correctly. Do I want atoms of nitrogen in my numerator?
No. But it can't.
It does cancel.
Do I want atoms of nitrogen in my answer?
No.
No. So what should happen to it? It had better cancel. Is that the correct location for my 6.022? Yep. Awesome. What am I relating that to?
1 mole.
1 mole of
Nitrogen.
nitrogen. Cool, moles, and I didn't, making my own stupid mistakes. Nitrogen and nitrogen. What would my answer be?
Well, you have moles.
I have moles.
You don't have grams. You don't have grams. You
I have mass units, right? Okay, what is our conversion factor between mass units and grams?
Inverse of Avogadro's one.
Sort of. I actually want to skip that for the moment. That, yep. 1.66 times 10 to the negative 24 what?
grams.
Grams was 1 atomic mass unit. Notice that I dropped the A because that was part of that unit system. Well, that looks like a really big calculation. Okay, so I'm going to try this. 14.076. Carry the 4.
12.6.
Divide by 2. And we end up with what? Really? I don't believe Mike.
We
Mike,
haven't-
there's no way I could do that in my head, right? Test it.
We haven't taken out the bottom one.
Yeah, we did.
Oh.
Bottom AMU technically came out over here. Remember, we
Oh,
swapped
I
that
see.
A.
Come on.
So Avogadro's number times its inverse is going to be 0.
These are inverses of each other. They don't multiply out to be 0, they multiply out to be 1. Why did we pick Avogadro's number? Avogadro's number is established to convert AMUs and grams up to a scalable measurement. That means when I look at the periodic table, yes, I can see the atomic mass unit. Nobody wants to work with the atomic mass unit. We don't measure in atomic mass units. We want to work in, say, grams or kilograms. If we used the atomic mass unit and even converted it into grams, that's going to be a crappy small number that we can't manipulate. So we invent a system to scale the reaction upwards or scale our measurement upwards. That's our Avogadro's number. And it scales up exactly to counteract the mass conversion, such that the number on the periodic table for mass is an atomic mass if I want to reference atomic mass units. Okay? It is also the mass for a mole of that atom.
In grams.
That is the mass of the mole for that atom, the units for our mass would be grams. So when I look at the periodic table and I want to know the mass of hydrogen, okay, it is 1 point, Jiminy Christmas, enough sig figs, right? 1.00795 AMUs. When will you ever work with a single atom of hydrogen? No. Will you ever be able to measure that AMU? No balance measures AMUs, okay? So that's a useless unit measurement. But if I turn that into 1.00795 grams for 1 mole of hydrogen atoms, now I'm looking at not manipulating a single atom of hydrogen, I'm looking at manipulating 6.022 times 10 to the 23rd atoms of hydrogen. I've scaled that system up so that it is now measurable. Avogadro's number merely takes things that we can't measure and makes them measurable. It's a beautiful system. Right? This is why most chemists run around saying, oh, it's mole day, which was like 2 days ago. Yay, I had like 3. Hey, happy mole day. Not quite screw off, but okay. I tend to think, yes, that's really powerful, okay, but how often am I going to use 6.022 times 10 to the 23rd?
A lot in this class.
Not even really in this class. We make this big deal about how useful it is. It is useful to scale our periodic table into grams per mole. That's about all it does. Once we're in grams per mole, guess when we use Avogadro's number?
Never again.
Never again. So within Chapter 8, we will be using Avogadro's number to do these atom scaling factors. That's okay. Okay? We'll be using it for those atom scaling factors, and that's about it. After that, we start using grams and moles. Okay? So with that, we'll go ahead and end.